Hey guys, my name is IBM and I'm still explaining solutions to a topic called quantum physics. This is for Physics 9702 paper 4. These are past paper questions. If you want the document with the questions, find it in the video description. Of course, I've solved circular motion, gravitational fields, electric fields, magnetic fields, and electromagnetic induction. I've also solved astrophysics, and I'm solving quantum physics. All these topics have typed solutions which you can find. If you want, you can write to me and you get them. If you want a document in the video description which has typed solutions, for the typed solutions it looks like this. It has clearly typed solutions like this. The solutions have been highlighted and clearly explained at every step with detailed solutions. Alternative answers have continuously been given that you can find in the video description. Okay, so this is part 8. This is part 8 of quantum physics. So I think in part 7 we stopped on question 2021. So in part 8, I want us to start from question 22. In an experiment, electromagnetic radiation of frequency F is incident on a metal surface. The results in the figure 10.1 show the variation with the frequency F of the maximum kinetic energy, Emax, of electrons emitted from the surface. So the results are showing the variation with the frequency F of the maximum kinetic energy. Determine the work function energy in joules of the metal used in the experiment. So we know from Einstein's photoelectric equation, we know that energy of a photon, which is given as HF, is equal to the work function energy phi plus the maximum kinetic energy Emax. And of course, from the graph, if we try to prolong this line, from the graph, if we try to prolong this line, I think it is somewhere here. And on this, using the scale is 0.5 divided by 10, which is 0.05. So this is 5.45. I think that's 5.45. So F naught, that is the threshold frequency. F naught is 5.45 times 10 to the power of 14 hertz. So if I want to find the work function energy, remember the work function energy, the energy of a photon is equal to the work function energy when Emax equals to 0. So when Emax equals to 0, the energy of a photon is equal to the work function energy. Therefore, the energy of a photon is going to be equal to h times F naught, where F naught is the threshold frequency. So this is going to be Planck's constant, 6.63 times 10 to the power of minus 34. Then times 5.45 times 10 to the power of 14. And from my calculator, I have 6.63 exponent minus 34, then times 5.45 exponent 14. So this gives me 3.61 times 10 to the power of minus 19 in joules. So that's the work function energy. So 3, you can write two significant figures because they didn't specify the number of significant figures here, but F is given two significant figures, or you can write three significant figures, that is 3.61 times 10 to the power of minus 19 joules. The work function energy in electron volts for some metals is given in the table. Determine the metal used in the experiment, show your working. So the work function energy for some metals is given here. So we just need to change this into electron volts to see which one is very close to it. So the work function given is equal to 3.61 times 10 to the power of minus 19. We change it to electron volts. So 1 electron volt is 1.6 times 10 to the power of minus 19. So I'll just divide 3.61 by 1.6. That is 2.26. To three significant figures, that is 2.26 electron volts. Therefore, the metal given here is potassium. So the metal is potassium. The intensity of the electromagnetic radiation for one particular frequency in B is increased. So intensity is increased. Set and explain the change, if any, in the maximum kinetic energy of the electrons. So the intensity has been increased. Of course, kinetic energy of the electrons depends on the photon energy, and the photon energy does not depend on intensity, instead it depends on frequency. Therefore, maximum kinetic energy of electrons cannot be affected. So I would simply say that kinetic energy depends on frequency. On frequency, not intensity. Kinetic energy depends on frequency, not intensity. Therefore, each photon has the same energy. Each photon has the same energy, so no change. No change to kinetic energy. There will be no change to the kinetic energy because kinetic energy only depends on frequency and not intensity. Then the rate of emission of electrons, of course, increasing the intensity means that more photons are incident on the surface per unit time. Therefore, the rate of emission increases. So, increasing the intensity means that there will be more photons arriving on the surface per unit time, so the rate of emission increases. So the rate of emission increases if the intensity increases. 23. A pi-zero meson is a subatomic particle. A stationary pi-zero meson, which has 2.4 times 10 to the power minus 28 kilograms, decays to form 2 gamma ray photons. The nuclear equation for this decay is pi-zero giving us 2 gamma photons. Explain why the 2 gamma ray photons have the same energy. Of course, remember, energy of a photon is equal to momentum times c. Since c is a constant, and initially the momentum was initially the particle was at 0. Initial momentum was equal to 0. It means the final momentum should also be 0. Because c is a constant, it's only the energy which is going to determine the momentum. Therefore, if the energy is not the same for each particle, then total momentum cannot be 0 again. So they should have the same energy and also moving in the opposite direction, so that they have the same momentum but in opposite directions, so that the total momentum is also zero. Therefore, we shall say that initial momentum is zero. To conserve momentum, the momenta of the photons should be equal and opposite. To conserve momentum, the momenta of photons should be equal and opposite. Should be equal and opposite. Since photons have the same momentum, they have the same energy. They have the same energy. We have seen that energy is equal to momentum times C for a gamma photon. Determine for each gamma ray photon the energy in joules. So we know that energy of the pi meson, or energy of the particle, is giving us 2 gamma photons, so it's going to be equal to energy of 2 photons. And so the energy of the particle, because the particle has mass, so its energy is going to be mc squared, or delta mc squared. That is from Einstein's equation, energy is mc squared. So this is going to give us 2 photons, and this is going to be twice the energy of 1 photon. So that means the energy of 1 photon is going to be equal to mc squared divided by 2. So this is going to be, they give us the mass. The mass is 2.4 times 10 to the power of minus 28. So that is 2.4 times 10 to the power of minus 28. Then times the speed of light, 3 times 10 to the power of 8, but this should be squared. And this should be divided by 2. Then from my calculator, 2.4 exponent minus 28 times 3 exponent 8 squared. That is 2.16 divided by 2. That's 1.08 times 10 to the power of minus 11. Then the wavelength. We know that energy is equal to hc divided by lambda. So the wavelength is going to be equal to hc divided by the energy, which when we substitute, h is 6.63 times 10 to the power of minus 34. Then times 3 times 10 to the power of 8. Divide this by the energy, which is 1.08 times 10 to the power of minus 11. So I have that 6.63 exponent minus 34 times 3 exponent 8, then divide by the answer. So that's 1.84 times 10 to the power of minus 14 meters. Then determine the momentum. We already know that a momentum of a photon is equal to h over the Broglie wavelength. So this is going to be 6.63 times 10 to the power of minus 34 divided by the wavelength, which is 1.84 times 10 to the power of, um, sorry, this is power minus 14. Power minus 14. A wavelength cannot be power positive 14 for a photon. So power minus 14. So I'll check with my calculator. I'll just simply say 6.63 exponent minus 34 divided by 1.84 exponent minus 14. So that's 3.60 times 10 to the power of minus 20. When four experiments are conducted to investigate the photoelectric effect, it is found that on exposure of a metal to light, either electrons are emitted immediately, that is instantaneous emission, or they are not emitted at all. Suggests why this observation does not support the wave theory. Of course, the wave theory would predict that there is no need for instantaneous emission. For it would suggest that whether the photons have less energy, if we were to shine them onto the metal surface for a long period of time, maybe an electron would accumulate enough energy from different photons continuously, and then with the time, when the energy is enough, then it should be emitted, or an electron should be ejected. Unfortunately, this does not happen. For, for a wave, if electron was, if for a wave, an electron, that is, if electromagnetic radiation was acting as a wave, an electron would, or an electron can, collect and accumulate energy continuously. And accumulate energy continuously. The spelling of continuously is lacking. Continuously, and will always be emitted at all frequencies, even after sufficiently long delay. Even after sufficient, it doesn't need to be instantaneous. According to the wave theory, it predicts that an electron can collect energy continuously until it is enough for it to be emitted, even after sufficiently long delay. Unfortunately, this does not happen in practice. This does not happen in practice. Observations show that whether you shine light of low frequency onto a metal surface for the whole year, as long as the photon energy is less than what is just enough to eject an electron, electrons are not ejected. But if you shine light which has high enough energy, or photons have high enough energy onto the metal surface, emission of electrons is instant, or is immediate. There is no time delay. Data for the wavelength lambda of the radiation incident on the metal surface and the maximum kinetic energy in K of the emitted electrons are shown below. Without any calculation suggests why no value is given for Ek for radiation of wavelength 650 nanometers. So wavelength of 650 nanometers, there's no value given for kinetic energy. Maybe this wavelength is above maybe this wavelength is above the threshold, because remember there is a maximum wavelength above which no photoelectric emission occurs. Therefore, we cannot talk about kinetic energy when electrons have not been ejected. So this could be above the threshold wavelength. So I could say could be lambda could be longer. Lambda could be longer than or greater than the threshold. The threshold wavelength. So no electrons. So no electrons emitted. Maybe there are no electrons emitted, or you could say frequency could be below the threshold frequency, because when lambda is above the when the wavelength, or let me say 650, is could be longer than the threshold frequency, so no electrons are emitted. Or you would say frequency. Could be below the threshold. So there is a minimum frequency below which no photoelectric emission occurs, and that minimum frequency is called the threshold frequency. So a longer wavelength is equivalent to a minimum frequency or a smaller frequency, since they're inversely proportional. Also note that work function energy is hf, which is hc over lambda naught. So I can also explain this in terms of work function, and I would say the photon energy is less than the work function. If the photon energy is less than the minimum required to release an electron from a metal surface, then we don't expect photoelectrons to be emitted, and therefore we cannot have a value for kinetic energy when there are no photoelectrons emitted. Use data from the figure 7.1 to determine work function energy of the surface. Okay, so we know that from Einstein's equation, the energy of a photon, call it E, is equal to the work function energy, call it phi, plus the maximum kinetic energy, called E max. So the energy of a photon is given as hc over wavelength is equal to the work function energy plus the maximum kinetic energy E max. So that means the work function energy is equal to hc divided by lambda minus E max. When I make a substitution, h is 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by 240 nanometers. So that is 240 nanometers, that's times 10 to the power of minus 9. Then minus maximum kinetic energy is given as 4.44. So that is 4.44 times 10 to the power of minus 19. In my calculator, I have the 6.63 exponent minus 34, then times 3 exponent 8 divided by 240 exponent minus 9. Then I subtract 4.44 exponent minus 19. This gives me 3.85 times 10 to the power of minus 19 joules. Radiation of wavelength 240 nanometers, so that's wavelength, gives rise to maximum photoelectric current I. The intensity of the incident radiation is maintained constant. So I is constant. So the intensity is constant. So I is taken for current. The intensity is constant. And the wavelength is now reduced. The wavelength is now reduced. So lambda is now reduced. Set and explain the effect of this change on the maximum kinetic energy of photoelectrons. So because the intensity is maintained constant, the radiation of wavelength gives rise to a maximum current of that. The intensity is maintained at a constant. The wavelength is now reduced. So we know that from Einstein's equation, maximum kinetic energy or energy of a photon is hc over lambda is equal to phi plus Emax, which means that the maximum kinetic energy is equal to hc over lambda minus phi. Of course, phi is a constant, h is a constant, c is a constant. The wavelength is now reduced. So lambda is reduced. That means maximum kinetic energy is going to be bigger. Because if lambda is made smaller, this quantity here becomes bigger. So maximum kinetic energy is going to be bigger. So reducing the wavelength means photon energy is now increased. And therefore it means, because remember photon energy is hc over lambda. So reducing wavelength means photon energy is now greater. And for the same work function, it means the maximum kinetic energy is now larger. So reducing wavelength means photon energy is now larger, and for the same work function, maximum kinetic energy is now larger or greater than the maximum photoelectric current I. So we have already answered a similar question in the past, but just for us to be very, very careful with this. So let us say I'll use a different letter for intensity, even though I'm used to using I. So we know that intensity is equal to power per unit area. And power is equal to energy over time, but total energy of electromagnetic radiation is equal to the number of photons times the energy of each photon, which is hc over lambda, then divide by time. This alone is power. Then we divide by area to find the intensity. So this means, therefore, this is the same as N over T times Hc over lambda times A. That is our intensity. But remember, the intensity is constant. So I'm going to make N over T the subject. So N over T, making it the subject, is going to be equal to the intensity, then times the wavelength, times the area, then divide by Hc. So the intensity is constant, area is a constant, H is a constant, C is a constant. That means reducing the wavelength is equivalent to reducing the number of photons incident on the surface per unit time. Of course, now that the photons have greater energy, only a small fraction of photons can be incident on the surface area per unit time. And of course, if fewer photons are incident on the surface per unit time, then it means the number of electrons ejected will also be smaller. Remember, it is a one-to-one interaction. One photon ejects only one electron. Therefore, the photocurrent I decreases. So we can say at constant intensity, at constant intensity, a higher photon energy means fewer photons per unit time. Fewer photons per unit time arrive on the surface. So the maximum photoelectric current is smaller, or it decreases as illustrated there. Okay, so I want part 8 to stop there. See you in part 9. Bye bye.